In this video lesson, you will learn about something called reaction stoichiometry. In order to understand this, you need to bring back in your memories the concept of moles as well as balanced chemical equation. So what exactly is reaction stoichiometry? Let's take an example. Suppose you want to bake Milo cookies. Now remember, in order to be a good chemist, you need to be a good cook as well. You need to know how to mix things in the right proportion so that the food tastes yummy. So let's take a look at some of the ingredients required to bake the Milo cookies. You need butter, caster sugar, flour, of course Milo, and egg beaten. Suppose you want to bake 28 cookies. So let's take a look at the masses of each ingredient required. You need 125 grams of butter. You need 1 cup of caster sugar, 1.5 cups of flour, 0.5 cups of Milo, and 1 egg beaten. Okay, now let's say you want to make 56 cookies. In this case, you will need 250 grams of butter, 2 cups of caster sugar, 3 cups of flour, 1 cup of Milo, and 2 eggs beaten. So what you see here is that when you double the amount of cookies, you need to simply double the amount of each ingredient required. In fact, this is what reaction stoichiometry is about. It helps us to figure out how much quantity of reactants are needed to get a certain quantity of products in a chemical reaction. Is there a minimum quantity of any reactants required? What happens if we have something in excess? The question is, how do we figure out all these? Well, the answer lies in a balanced chemical equation. You can think of it as a recipe that allows us to figure out how much reactants are needed to get product of certain quantity. Now, the coefficients in a chemical equation can be interpreted either in terms of molecules or in terms of moles. In fact, it's more convenient to talk about moles. Let's say you have a chemical reaction in which a reactant A is giving a product B. Now you want to estimate how much of A is required to give a certain quantity of B. Now let's look at the different steps of calculation. Step 1, if you know the molar mass of A, you can convert the grams of A to moles of A. Step 2, you need to use a balanced chemical equation to estimate how many moles of A get converted to moles of B. And finally, if you know the molar mass of B, then you can convert the moles of B to grams of B. Let's take a look at an example. Propane, C3H8, is normally a gas, but it is sold as a fuel compressed as a liquid in steel cylinders. The gas burns according to the following equation: C3H8 plus oxygen giving carbon dioxide and water. How many grams of carbon dioxide are produced when 20 grams of propane is burned? Now, in order to solve this problem, you need to first have a balanced chemical equation. So let's start by balancing the chemical equation. If you look carefully, you have 3 moles of carbon on the reactant side, whereas you have 1 mole of carbon on the product side. So let's try to balance out the carbon. We can simply do that by adding a 3 over here. Now let's take a look at the hydrogen. Now there are 8 moles of hydrogen on the reactant side, whereas the product side has only 2. So in order to balance the hydrogen, you simply need to add a 4 over here. Now let's look at the oxygen. Now there are 2 moles of oxygen on the reactant, whereas on the product side, there are 10 moles of oxygen. So in order to balance the chemical equation, you need to add a stoichiometric coefficient of 5 in front of oxygen. So now we have a balanced chemical equation. Now let's proceed to the next few steps. We first start by calculating the molar masses of the reactants. Let's calculate the molar mass of propane, which is going to be around 44.094 grams per mole. Remember, you need to use the atomic masses of carbon and hydrogen to figure out the molar mass. Similarly, for carbon dioxide, the molar mass is going to be 44.01 grams per mole. Step 2, we need to figure out the number of moles that are present in 20 grams of propane. To do the calculation, you simply have to divide the mass of propane, which is 20, by the molar mass of propane, which is 44.094. If you do the calculations, the number of moles of propane is going to be around 0.454. Now let's take a look at the reaction stoichiometry. So 1 mole of propane produces 3 moles of carbon dioxide. So therefore, the number of moles of carbon dioxide that are produced in this reaction can be calculated by multiplying 0.454 moles of propane with 3 moles of carbon dioxide. And the answer is going to be 1.36 moles of CO2. Finally, we need to estimate the mass of carbon dioxide that is produced. And you can simply obtain this by multiplying the number of moles, which is 1.36, by the molar mass of carbon dioxide, which is 44.01, and the final answer should be 59.9 grams of carbon dioxide that is produced in this chemical reaction. Now let's go through a few more important concepts in reaction stoichiometry. Now, when dealing with chemical reactions, you will often come across something called a limiting reagent or a limiting reactant. Now, in a chemical reaction where there are 2 or more reactants, it's possible that one of them gets consumed first. The reactant that gets consumed first is called the limiting reagent. The other one is said to be in excess. In fact, it is the limiting reactant that determines how much of the product is going to be formed. So the question is, how do you determine which is a limiting reactant in a chemical reaction? So here's what you need to do. So for each reactant in the chemical reaction, you need to determine the mass of product formed from each one of them, assuming it's completely consumed. Whichever reactant gives the smallest mass of the product is called the limiting reactant. Perhaps it will be more clear if we go through an example. Zinc metal reacts with hydrochloric acid by the following reaction. Zinc plus HCl giving zinc chloride plus hydrogen. A 0.3 moles of zinc is added to hydrochloric acid containing 0.52 moles of HCl. How many moles of hydrogen are produced? Which is the limiting reactant? Well, we have to start by balancing the chemical equation. If you look carefully, in order to balance this equation, we simply have to add a stoichiometric coefficient of 2 before HCl. So now we have equal masses of zinc and chlorine and hydrogen on both sides. That means the remaining reagents will have a stoichiometric coefficient of 1. Okay, now let's proceed to the next few steps. From the reaction stoichiometry, we can see that 1 mole of zinc produces 1 mole of hydrogen, whereas 2 moles of HCl produces 1 mole of hydrogen. So now we have to determine how many moles of hydrogen are formed from zinc and HCl. So let's start with zinc. So the number of moles of H2 produced from zinc can be calculated by multiplying the number of moles of zinc with the number of moles of hydrogen that are produced from 1 mole of zinc. And if you do the math right, it's going to be 0.30 moles of hydrogen. Now let's do the same with HCl. So the number of moles of H2 that is produced from HCl is given by 0.52 moles of HCl times the number of moles of hydrogen that is formed from 2 moles of HCl. And if you do the math right, the answer will be 0.26 moles of hydrogen. And therefore, we can see that HCl gives the least amount of hydrogen, and therefore it is the limiting reagent. Now let's talk about another terminology of reaction stoichiometry. It is called the theoretical yield. It is the maximum amount of product that you can get from a reaction from a certain amount of reactants. In fact, it is the same amount that you calculate based on the limiting reagent. However, in reality, the actual yield is much less compared to the theoretical yield. And there can be several possible reasons for this. For example, you may be losing some of the products. There may be some side reactions happening at the same time and many more. So therefore we define another parameter called the percentage yield, which is the actual yield expressed as a percentage of the theoretical yield. Now let's go through an example. Silicon carbide SiC is an important ceramic material made by reacting sand, which is silicon dioxide SiO2, with powdered carbon at high temperature. Carbon monoxide is also formed. So when 100 kilograms of sand is processed, 51.4 kilograms of silicon carbide is recovered. What is the percentage yield of silicon carbide from this process? We have a balanced chemical equation for this reaction. So we have 1 mole of silicon dioxide reacting with 3 moles of carbon to give 1 mole of silicon carbide and 2 moles of carbon monoxide. So with this balanced chemical equation, we can proceed to the next few steps. Now let's start by calculating the molar mass of silicon dioxide, which is 60.09 grams per mole based on the atomic masses of silicon and oxygen. In step 2, we need to calculate the number of moles of silicon dioxide that are present in 100 kilograms. So you take the mass of silicon dioxide, which is 100. We need to do a unit conversion here. So we multiply this by 1000 grams divided by the molar mass of silicon dioxide, which is 60.09 grams per mole. If you do the calculations, the number should be around 1664 moles. Now let's assume 100% conversion of the reactants. That means we need to find out what is the maximum mass of silicon carbide produced, which is the same as its theoretical yield. Now based on the reaction stoichiometry, 1 mole of silicon dioxide gives 1 mole of silicon carbide. So the number of moles of silicon carbide that are produced is 1664 moles. Now if you want to convert this to mass, you need to multiply this by the molar mass of silicon carbide, which is 40.1 grams per mole. Now after doing the math, the number should be around 66.73 kilograms of silicon carbide. Now we need to do one more step. Now the actual yield of silicon carbide is 51.4 kilograms. So the percentage yield of silicon carbide equals to its actual yield divided by the theoretical yield times 100. So now let's plug in the numbers. So the actual yield is 51.4. The theoretical yield is 66.73 times 100, and this number should be around 77%, which is the percentage yield of silicon carbide. Now this brings us to the end of this video lesson. In the next video, we will go over one more problem on reaction stoichiometry.